So we are going to move to the next speaker, who is Miss Chao Wen from Soochow University. Miss Chao Wen is a master student at the physics degree in master. And we included her, despite she is master student, in this presentation because in this symposium, because she won the 2020 Park AFM scholarship. So that's why we wanted to give her the opportunity to show her work. And the title of her presentation is Calcium Fluoride, an Outstanding High K Dielectric. So Chao, when you want, you can start.
So my name is Chao Wen, and I'm a master student at Professor Marland's group from Soochow University. As mentioned by Professor Gianos and Dr. Rajan, two-dimensional materials are very important for electronic devices. And here, I'm going to talk about calcium fluoride, which is an outstanding high-K dielectric that is compatible with 2D material-based electronic devices. And I will divide my talk into 4 parts. In the first part, I'm going to introduce some background information of our research work. Then, I'm going to talk about the morphological information of our calcium fluoride layer. After that, I'm going to talk about several experiments to analyze the electrical properties of calcium fluoride at nanoscale. And the final part is a conclusion. So, dielectrics are very essential for microelectronic devices. The first is a dielectric is silicon dioxide. But when the size of the devices has been scaled down, leakage currents arise across the thin silicon dioxide film, increase the power consumption, and reduce the reliability of our microelectronic devices. So, high-K dielectrics are introduced to replace silicon dioxide in order to reduce the leakage current. The downscaling process also requires other new materials, for example, two-dimensional material, graphene and molybdenum, to replace the traditional channel. But the interface between this 2D channel and 3D dielectrics is always problematic because there are plenty of dangling bonds on the surface of these 3D dielectrics. In order to solve this problem, we introduced layered dielectrics such as hexagonal boron nitride, as mentioned by Dr. Alok. And we could find that when we introduce hexagonal boron nitride, this layered dielectrics, we have a very clean interface between layered channel and these 2D dielectrics. But for hexagonal boron nitride, it only has a small energy band gap of 6.08 electron volt and the low dielectric constant, which is quite similar to that of silicon dioxide, 3.5. Compared to hexagonal boron nitride and silicon dioxide, calcium fluoride has a larger energy band gap of 12.1 electron volt and a higher dielectric constant of 8.43. More importantly, the calcium fluoride 111 surface is terminated by fluorine atoms, so it is chemically inert. The inert nature of calcium fluoride 111 surface can ensure a heteroepitaxy growth of two-dimensional material on top of 3D calcium fluoride bulk crystal. Next, we read the work from in Nature Electronics, in which they introduced the calcium fluoride layer into the molybdenum-based field effect transistors. Basically, they transferred the molybdenum, which is grown by CVD, onto the calcium fluoride surface. And the device they fabricated show a very small hysteresis and a large onboard of current ratio, close to 10 to the 7th order. But here I want to point out that although the device performance is very promising, the nanoscale information they provided in the Nature Electronics paper is very limited and rather poor. So we are very curious about the microstructure of our calcium fluoride and also the electrical properties of them. So first, we analyze the morphological information of calcium fluoride using cross-sectional transmission microscope, which I will refer to as SThM in the next talk. And here is a scanning SThM image. The calcium fluoride is grown on top of N-type silicon by molecular beam epitaxy at a temperature of 250 degrees centigrade. And from the EDX map, we can see the clear element distribution of the two elements, calcium and fluorine, in the middle. On top of calcium fluoride, we deposit chromium as a protective layer. So in the EDS map, we have a lot of chromium elements. The deposition of chromium introduces oxygen. So this is the reason why we also have a lot of oxygen elements. Below the calcium fluoride, we have silicon substrate. So here we have a lot of silicon elements. And from EOS profile on the right, we can see that the blue line represents the element calcium and the purple line represents the element fluorine. We can see two obvious peaks of these two elements, which further confirm the right chemical composition of our stack: chromium, calcium fluoride, and silicon. Next, we took over 56 sub-nanometer resolution TEM images with a total length of 2 micrometers. Here, we have a layered pattern with a length of 16.8 nanometer. We can see that our calcium fluoride has a total thickness of 2.53 nanometer with an interlayer distance of 0.32 nanometer. Here, I want to point out that in the Nature Electronics paper, they also claim that the interlayer distance is around 0.32 nanometer, but their unclear TEM image is not enough to support their claim. But in our paper, in this TEM image, it's much more clear that the interlayer distance is around 0.32 nanometer. And next, when we zoom in, we could find different patterns. First, we have the hexagonal pattern, and second, we have the cubic pattern, and third, we have the point-like pattern. The existence of these different patterns are related to the angle of crystal orientation with respect to the electron beam in the TEM. And very interestingly, these patterns are one another very smoothly without any visible defects. After the TEM image, we measured the surface of our calcium fluoride stack with atomic force microscope, which I will refer as AFM later. Here, that the surface of our calcium fluoride is very flat with a roughness value of only 54 picometer, which is consistent with the height plot below. We also measured the morphological information of other three examples we will use later for comparison of the electrical properties. The first one is 4.7 nanometer silicon dioxide grown by thermal oxidation at infinite technologies. The second example is titanium dioxide grown by atomic layer deposition. From the AFM maps, we can find that the surface of these two examples are very flat with a roughness value less than 200 picometer. From the TEM images, we can find that these two oxide layers are amorphous and there is almost no thickness fluctuation. The third example is hydrogen boron nitride fabricated by chemical vapor deposition. We can find that the roughness value is a bit larger than 400 picometer, but is still very flat. From the TEM image, we can find that the hydrogen boron nitride has a clear layer structure, but with amorphous defects. Here, I want to compare the TEM images in hydrogen boron nitride and calcium fluoride. On the top, we have a TEM image of the CVD grown hydrogen boron nitride. We can find that we can see the clear layered structure, but with a length of around 20 nanometer, we have 5 amorphous defective regions. But in hydrogen boron nitride, we have a total length of around 30 nanometer, and we have different patterns. Here is the layered pattern, here is the cubic pattern, and here we have the hexagonal pattern. These patterns merge into one another very smoothly without any visible defects. The difference of the TEM images will contribute to the different electrical properties, which I will discuss about them later. So next, I start to measure the electrical properties of our calcium fluoride layer at nanoscale using atomic force microscope. And before I start, I would like to introduce our AFM. The AFM we use is NX high-vac AFM from Park Systems. It has 4 main advantages. First, it can work in a vacuum atmosphere down to 10 to minus 6 torr. Second, we can use a logarithmic preamplifier to measure the currents from picoamperes to milliamperes. Third, we can measure our sample at high temperatures up to 600 degrees centigrade. Fourth, we can connect the CAFM with a semiconductor parameter analyzer so that we can apply pulse stress to our samples. So with this wonderful CAFM, at first, we measure the current maps in our 4 stacks: calcium fluoride, silicon dioxide, titanium dioxide, and hydrogen boron nitride. We can find that in these current spots, in these current maps, we have these rare current spots. These rare current spots are the electrically weak spots in our 4 stacks. And below the current maps, we have the histogram distribution of the spot area. And we can find that compared to silicon dioxide, titanium dioxide, and hydrogen boron nitride, the distribution of the current spot area in calcium fluoride is the narrowest one. And we also calculate the mean radius of these current spots in these current maps. And we can find that the mean radius in calcium fluoride is only 3.7 nanometer, while in other 3 examples, the mean radius is much larger. In hydrogen boron nitride, the mean radius is around 14.48 nanometer, which is as triple as that in calcium fluoride. So next, I start to measure the current versus voltage curves in calcium fluoride, which I will IV curves later. And before the IV curves, I first scan the surface with a scan size of 20 micrometers. Then I select a matrix of 100 points. After that, I do 1 IV curve at each position. So in total, I got 100 IV curves in calcium fluoride. And it is very interesting that these 100 IV curves show very low variability from one position to another. Also, these IV curves show that the current rises abruptly with very low leakage current. And our calcium fluoride only has a thickness of 2.5 nanometer, but it has a large onset potential of larger than 60 volts, which means that our calcium fluoride stack is of high dielectric strength. Later, we produce the experiments in calcium fluoride. We also reproduce the same experiments in silicon dioxide, titanium dioxide, and hydrogen boron nitride. Here, I want to point out that in the paper published in Applied Physics Letter, which is written by Professor James Home, they only presented 1 IV curve for each thickness, but here I presented over 200 IV curves, 280 IV curves in each stack, which means that our results are more reliable. And from these 4 IV plots, we can find that only the IV curves calcium fluoride show an abrupt increase of current with very low leakage current. In silicon dioxide, titanium dioxide, and hydrogen boron nitride, the current rises very progressively with the increase of tube bias. So this means that in calcium fluoride, the abrupt increase of current is very unique. Later, we calculate the onset voltage in calcium fluoride with a threshold current of 100 picoampere and made a histogram distribution in our 4 stacks. And we can find that the dispersion of onset voltage in calcium fluoride is the narrowest among 4 samples. We also calculate the mean value of the onset voltage and the standard deviation of our onset voltage. And we can find that the IV curves in calcium fluoride show the lowest variability from one location to another. Then we calculate the onset voltages in these 4 stacks with different threshold currents, 5, 10, 20, and 100 picoampere. And we can find that only the onset voltages in calcium fluoride always keep in the same line, which is when we apply different threshold currents, which is consistent with a sharp increase of currents in the calcium fluoride IV plot. In other 3 examples, silicon dioxide, titanium dioxide, and hydrogen boron nitride, the onset voltage does not keep in the same value, which is consistent with their progressive increase of currents, shown in the IV plots. So next, I measure the IV curves of around 2 nanometer silicon dioxide. This thickness is quite similar, quite close to our 2.5 nanometers calcium fluoride layer. Here, I want to point out that our silicon dioxide wafer, 2 wafers, A and B, are both grown by thermal oxidation at infinite technologies. So this means that our silicon dioxide wafers are of good quality. But when we look at the IV curves, we find that the IV curves show very small onset voltages compared to calcium fluoride, and the variability is much larger. Here, I want to point out that all the IV curves we measured just now use a linear amplifier, so we can only observe the current from picoampere to 10 nanoampere. In order to observe the current from microampere to milliamperes, we change the linear preamplifier to the logarithmic preamplifier, and we reproduce the experiments in calcium fluoride and silicon dioxide. We can see that in calcium fluoride, first, the current stays at noise level. When it goes to a region of around 0.6 to 8 volt, it has a sudden increase of current. And here, we only have one part of current that is caused by breakdown. But in silicon dioxide, we have two parts of current. At first, the current stays at a noise level, and then it has a progressive increase. Then it has a sudden increase, and here the currents are divided into two parts. In the first part is caused by leakage current. The second part is caused by breakdown current. Here, in order to confirm that in calcium fluoride we really have the breakdown, we perform one experiment, which is use different current limitations. So, with a small current limitation of 1 nanoampere and 10 nanoampere, the current goes back to the noise level before the tube bias goes back to 0. But with a larger current limitation of 1 microampere, we can find that the current stays at a high value even when the tube bias goes back to 0. So this means that with a larger current limitation, we have breakdown. And so, of course, when we do not apply any current limitation, of course, we have breakdown here. And the current here is only caused by breakdown. So next, we find that we can decide the breakdown size by changing different voltages. Here, we apply two different IV curves. The first one is from 0 to 8 volt. The second one is from 0 to 10 volt at two different positions. And we can find that with a voltage from 0 to 10 volt, we have a severe surface modification compared to the position where we apply 0 to 8 volt. So this means that the dielectric breakdown introduced epitaxy only occurs when the voltage keeps increasing after the dielectric breakdown. So later, we reproduce the same experiments in different positions, and we can find that with a ramp voltage stress from 0 to 10 volt, we always have much severe surface modification compared to those positions we apply 0 to 8 volt. So this means that the observation in the previous slide is reproducible. So finally, here comes to our conclusion. First, the high-resolution TEM images demonstrate that the cubic crystalline structure of ultra-thin calcium fluoride is continuous and almost defect-free over large regions, and this property prevents the formation of electrically weak spots as shown in the current maps. Second, our calcium fluoride stack shows the smallest size of weak spots as shown in the current maps, and ultra-low point-to-point variability, low leakage currents, as confirmed in the IV curves of calcium fluoride. Third, our calcium fluoride shows a high dielectric strength, much larger than silicon dioxide, titanium dioxide, and hydrogen boronitride. So finally, I would like to thank our collaborators, Professor Tibor Grasser, Professor Nikolai Sokolov, Professor Winifred Messenberg, and our group at Soochow Universities. I would like also thank Park Systems to provide such a wonderful AFM and select me to receive the Park AFM scholarship for this year, and Infinite Technologies to produce such good silicon dioxide examples. And that's all. Thank you. Any questions are welcome.
Thank you very much for the presentation. I wanted to ask, to read one of the questions that are here. So yes. The first one is, why the leakage current in calcium fluoride is very low or relative low when it is breakdown in page 16?
Yes. So here, actually, if we look at page 17, it will be much more clear because here we zoom the current from to show the current from 0 to 100 picoampere. In the previous slide, we showed current from 0 to 10 nanoampere. So in calcium fluoride, as we shown in the SThM image, we have different orientations, but these orientations merge into one another very smoothly. We didn't see any visible defects in our SThM images, but in silicon dioxide and especially CVD hexanoboron nitride, we can see a lot of amorphous defective regions. So those defective regions cause the electrically weak spots, which cause the leakage currents. Here we have a lot of leakage currents, but in calcium fluoride, the film is grown by molecular beam epitaxy and is of good quality and defect-free over large regions. That's it.
Okay, there is another question. Let me see. So the question is in page 13.
Yes.
Would you please explain how can one pattern of crystal structure switch to another without any defect, for example, grain boundary? Thank you.
Okay, so when we look at this image, we can see different patterns, and this merge into one another very smoothly because this is one special quality of the ionic crystals. And if we can see here, we do not see defects. Actually, here I didn't put any slide, but if you look at the grain boundaries present in hafnium dioxide or other materials, you can see that the grain boundaries are different. Here the only thing I can say is that thanks to the molecular beam epitaxy, it gives us an example. With larger regions, we do not see the grain boundaries. And the different orientations are related to the ionic crystal, the property of ionic crystal.
All right, there are a couple of more questions. However, I am afraid that we don't have more time. So I would like to thank you again for your nice presentation.